Welcome to Theme 4. Theme 4 diverges a little bit from the previous from the previous themes in that it is more of an operationally oriented. We're looking at comparing different orientations, operational modes for rover observation to get a better understanding of how we might be able to bring rover autonomy into the field of planetary exploration. So moving forward, please. Well, I thought I had a different title page. There's a large team here, and the original title page had a lot of other names in it, but unfortunately, I didn't see it there. So, well, a little about me, I guess. My main research interest has always been Mars and water on Mars, the history of Mars. But I'm also interested in in situ resource utilization, particularly as it will pertain to the Moon and Mars. I've been on several Mars missions, and lately I'm involved in the Viper mission, which is a rover that's going to go to the lunar poles and drill into under the surface to look for ices and organics and whatever else might be there. Anyways, let's go to the next page, please. So here's the premise. So today's robotic exploration is actually centered around the tight operator and robotic command and execution loop, meaning that there's always a team of operators that basically carefully instruct the rover on navigation and target selection. They're basically telling the rover, move 1 meter forward, turn this much, go 1 meter forward, point your camera there, take this image. And every single time you have a sequence of those commands, basically it has been a whole transmission cycle. They send the command, the rover does it. If it's supposed to acquire data, it acquires it and sends it back. The team then analyzes the data, sees that the rover did what it's supposed to do, sits down to make more decisions and planning, and then commands the rover onto the next set. So there's a few problems that come out of that. One is that it's dreadfully slow, right? It takes forever to accomplish anything. A single sample collection and analysis with MSL right now takes over a week. And that is after they have identified the place they want to obtain samples from. At the same time, if you try to send the rover on a long traverse, say move 150 meters because we know there's no rocks in the way from this target, from this location to another location of interest, the rover is going to go there blindly. In the meanwhile, there might be all kinds of things that a normal scientist could have seen as he or she was walking down to the next target location that the rover is going to completely miss, and therefore the team is going to miss. So the science can be impaired, or opportunistic science can be impaired by the fact that we're getting no information. No one's even looking at what happens between point A and point B. So let's go to the next slide, please. So we here are proposing a new paradigm. This was originally brought up by David Wettergreen and his team, and he will be talking more about this. So in this new paradigm, we don't uniquely tell the rover what to do at every step of the investigation. Instead, we give it open-end. Instead, the investigation is more open-ended, and the rover is able to respond to ongoing observations without any iterative feedback from an operator. And the way this is done, and David's going to go more deeply into this, is basically you have the scientists, which basically provides the rover with something called a hypothesis map. Basically, a pool of hypotheses of what the rover might see and what it should be testing for. Scientists can also give explicit commands, such as, for example, a specific path they wanted to go, specific targets it wants to go. And then the rover takes all this information, basically calculates a path, an optimal path to address all these observations in order to resolve the hypotheses. And then the rover basically performs the traverse and observations. Go to the next slide, please. So this is more in words of what I just showed there. Basically, we start on the left with the science team, basically obtains and analyzes remote sensing data of the field site. For example, this could be a combination of high resolution aerial imaging, topographic maps, or basically hyperspectral image cubes from which they obtain mineralogy. And they identify basically locations of interest. They generate what is called the hypothesis map. In this case, it would be basically the geologic origins, and they provide it to the rover, in addition, of course, to turn information so that the rover knows how to navigate. The team can also provide must-go locations if they have found places that look really interesting. Then the rover takes on and basically plans the traverse. For the rover, this is an optimization problem, right? It's what is the most efficient routes to cover the different targets of the hypothesis map, and also include the must-go locations if those have been requested. Then the rover performs the traverse and the measurements. It does not wait for the operators to tell it how far to move on every step. It basically does it itself. It has some degree of intelligence where it can recognize obstacles, and it knows basically what the local topography is, so it can plan out, so it can actually perform a safe traverse between waypoints. And periodically, or basically at specific intervals, or when it discovers something that was unexpected or new, the rover can stop and communicate back with the operators, provide them with a summary of the results, and and basically receive an updated hypothesis map if that is warranted. In this case, the rover is actually responding to observation it's performing, and because it's not bandwidth limited, in other words, it's not returning all the data to the Earth for analysis, it's doing its own analysis on board. It basically can actually perform a lot more observations and analyze them, and then select what are the most optimal observations to return to the operators. Next, please. So what we perceive would be advantages here would be, first, we would have improved operational efficiency, right? Since the hypothesis maps communicate the latest objectives simply, and identify the appropriate behaviors, the rover does not need to wait for instructions on every step of the way. And then we expect that there should be an improved science return, because the rover is going to be able to acquire a lot more data than it can transmit back to the Earth. So even as it's traversing from one point to the next, it is continually performing observations, which would have not been done in a more standard paradigm of rover exploration. Next, please. So throughout this talk, this was just introduction, we're going to talk about the software tools that are going to be used on the rover. This includes the hypothesis map, which David is going to talk about. It includes Such Recorder, which Roger has talked about. It includes hardware tools, which again is the Zoe rover. So both the hypothesis map and the Zoe rover are going to be talked in sequence by David. And then we're going to talk a little bit about the instruments. Tom Prettyman is going to talk about the GRS he's developed. And then I'm going to talk a little bit about the implementation, the field sites, and how these experiments will be performed. Next, please. Okay, this is where David starts.
Hello, are you able to hear me okay?
Yes.
Great. Amanda, you're going to display my slides, yes? So I'm David Wettergreen. I'm a research professor at Carnegie Mellon University. The first bit of work I'll be describing here has been ongoing for quite a while. We were initially supported under an NSF award to develop the basic ideas, the basic machine learning algorithms behind it. And we're able to get through some good simulation studies of results. And with support from TREX for myself and my doctoral students, we've done one preliminary field experiment, and we're planning for more experimentation coming up next year. So next slide. Yep. I think Eldar touched on most of this here. The idea that we're pursuing is for robots that are able to perform some of the decision-making that they need for exploration on board. We're not trying to replace scientists here. We're trying to make the robots more efficient, so they spend less of their time either waiting for commands or waiting for interpretation of the data that's been collected so that they could decide what to do next. So there's a nice study out from JPL on the difficulty of maintaining high productivity with the rovers. You know, we see their exciting results, but I guess most people don't think about the fact that most of the time the rovers on Mars and other systems now and in the future are just sitting there. They're just waiting, maybe charging their power, but they're not really using their instruments and they're not going anywhere. So to get higher productivity has been a challenge. And the reason has been that although these devices are good at autonomously collecting data, they don't really have a capability to interpret that data in order to make decisions. And therefore, they can't decide what to do next, and they have to wait for that guidance. So next slide. The approach that we're taking, Eldar alluded to this, is to try to give the robots, the robotic system, some guidance that's useful beyond a sort of specific prescription of what to do. So we want to convey information about the region and information about the scientific exploration that's ongoing so that they have that basis for making decisions. So we want to start with some kind of map. This could be a sketch, scientist sketch of, you know, the abundance of water expected in the area or the mineral distribution over an area. It could be low resolution prior information. So we have lots of sources of orbital or regional information that are not as precise as could be obtained on the ground, but it provides a good prior. So we want to use that information in a map in order to do planning, deciding where to make a measurement. And I'll talk in detail about how we decide the most effective place to take a measurement. But then once that measurement is made, or that observation is made, we want to update the model, the robot's model of the environment on board, hopefully in real time, so that the exploration can proceed and not have to wait for that interpretation of the data. Okay, so next slide. This puts together the idea of autonomous exploration, where as a robot moves through the environment, and here the movie you're seeing on the right is you know, the path of some theoretical robot exploring. This is actually a simulation that we did for Mars. We want to update that prior model and choose the places to sample that will best resolve any uncertainty or ambiguity in the model and provide the most useful and new information. So the way we do this is by applying information theory, and simply put, we're trying to reduce the entropy in the model, which is another way of saying we want to reduce the uncertainty in the most efficient manner. So the taking observations that most significantly reduce uncertainty in the model. Let's go on to the next slide. All right, so as I said, we want to start with some prior information. It can be a sketch. Most of the work that we've done so far, we did some work with Eldar sketching out some geologic maps for us, but mostly we have started with low resolution orbital information. So I'm not going to tell any of you about imaging spectroscopy, other than to remind that we are able to get these data sets that are covering large areas at low resolution, much larger areas than a robot could practically explore on its own. The data cube you see there is like a 10-kilometer cube. So it would take a very long time for a robot to go everywhere in that 10-kilometer cube. So we want to figure out how to explore part of it and learn the most we can over the large area. And of course, this is complicated by the fact that every one of those pixels is actually a mixture of all of the different minerals or materials that are there. So disambiguating what's going on the ground is something that Roger has talked about. And I'll explain how we get to the point where we can actually use tetracorder to build these better models. So next slide. In order to have a robot do something useful with the data that's measured by an instrument like the ASD spectrometer, or this data you're seeing here is from the Avarice instrument, it has to encode it in some form, and it has to have a way to extrapolate from individual measurements to the larger area. So we do that by applying some machine learning algorithms. Many people have heard of deep learning and sort of the magic that happens inside these deep networks. So we're trying to harness that magic by building a network that allows us to input spectra collected by the robot from the ASD spectrometer and encode that in a lower dimensional latent space. So what that means is we want to have a way to generalize that information, and we want to have a more compact representation that's been manipulated in ways to do things like normalization and decorrelation that allow us to reason about the extrapolation from one place in our map to another. We use something called the Gaussian process. Oftentimes, what's inside these deep networks is sort of, like I said, a ball of magic, but we've really tried to apply a principled representation here that then we can look at and understand how our encoding network is working. And we can also add additional information into that latent space, other spectra, other instruments, and so on. So that then when we decode the robot's representation, we get something like an accurate spectra out the other side. So in the upper right there, you see, oh, it's a little hard to see, but just to, there's the ground truth, the actual spectra collected on the ground. And then there's a prediction that the robot makes as it's collected more and more observations. So the robot's traveling, it's taking measurements. And as you see those green bands getting narrower and narrower, that's reducing the uncertainty. So it's basically saying that at those two sampled pixels, which are not locations that the robot ever measures directly, but at those two sampled pixels, our uncertainty on what the spectra is being reduced. Next slide, please. So this is a process called spatial spectral regression that David Thompson, who's a former PhD student of mine, now at JPL, has been working on for a while. And as I said, what we want to do is come up with a representation that it's a little difficult for us to understand, but the robot can understand this well. By putting into this feature space, it can do the type of analysis to determine where the greatest uncertainty is, so where another measurement would be most useful, and to extrapolate the measurements it does make to the larger region. Next slide, please. So once we've done this extrapolation, now we can perform what's referred to as experimental design, which is a scientist's way of saying deciding where to go next. What observation will be the next most useful thing. And the illustration you're seeing here on the right is a map of entropy. So that's the map of uncertainty. It starts out at a high value, the world is yellow, and as the robot progresses, the uncertainty reduces and goes to a darker value. So what's important to observe here is that path the robot is taking, which is marked out in the white dots, is only covering a small area, but it's covering a lot of diversity in the measurements it's making, which is why you see the entropy reducing over the whole area. Why in the upper right that entropy is dropping down dramatically? It's because the observations the robot made actually allow it to disambiguate the spectral signature there in the upper right. Okay, next slide. I see I'm going long on time, so I'll try to be quick here. We've run a number of different planning algorithms, so we're trying to come up with different methods of choosing the path of the robot, or more importantly, different methods of choosing the reduction in uncertainty to do that as efficiently as possible. And we've, as I said, we've done some simulation studies. Next slide, please. We've actually done these studies with real data. We've used the Cooperite Hills, Nevada site. Many, I think, on the field team are familiar with this site, but we have very high resolution data covering the whole site, which gives us excellent ground truth. And Rogers analyzed that data, I know, to give some accurate mineralogical maps of the site. But we can use that, and actually we reduce the resolution and add noise, but that's our initial hypothesis. And then in simulation, we've studied possible explorations of this site. And I'll just highlight 3 areas that we've looked at, and then we can go on to the next slide. The first thing we did was run about sorry, next slide.
Okay.
Nope.
Sorry.
We did about 100 different possible traverses, so 100 starting places, 100 end of, well, not goal locations, but distances of travel through the site. We ran different planners, and we measured the reduction in uncertainty of the model over these traverses. We also measured the reconstruction error, which is the difference between the model of geologic diversity that the robot ended up with compared to that ground truth geologic map. Go on to the next slide, please. And actually, I think let's skip the next slide. Yeah, this is again just showing how entropy is reduced and the prediction is improved throughout the map. So this is the important result from the simulation study. We showed a strong correlation between the reduction in entropy. So this is reduction in the robot's uncertainty of the geologic interpretation versus the actual ground truth. So that's a graph on the left, that's entropy versus error. So that gives us confidence that when the robot is taking actions that it believes will best reduce its uncertainty, that's going to correlate with producing the most accurate map. On the right, again, just shows graphs of performance of these different planning strategies. This work, as I said, was done in simulation. We now have about 7 different planners that we're running that we'll test out with TREX. And next slide. As I mentioned, we did do one preliminary field experiment, and all I'll say here is that the performance of the actual robot with the spectrometer at the Cooperite site follows. The lines aren't as smooth because there aren't hundreds and hundreds of runs, but they do follow the same results. And we believe we have an effective planning method here. Next slide. I think that's sort of mostly what I had to say here. We've proven out this method. We've got one preliminary experiment, and we're looking forward to further testing through TREX. And I'll note that the video on the right is showing a geologic map. I'll say a little bit more about that in the next talk. But for these initial experiments, we were using a simple classifier, basically 3 classes, linear classifier of the 3 dominant minerals at the site, not doing any of the mixing ratios that tetracorder is capable of. But again, we were able to show good reconstruction. And I think I should stop there. Next 2 slides are just making the point stronger.
But thanks, David. We can move on to the rover now.
Okay.
Oh, was that both?
So I'll report a little bit on our robot Zoe that the team will be using for upcoming field work. This is an old robot, 15 years old now, but still going strong. Hundreds of kilometers of field experience. Initially supported by NASA, developed through the A-STEP program, which then became the P-STAR program. It's served on many other NASA projects, and it's going to serve us as well. So next slide. I'll be pretty quick here, but I'm happy to answer any questions about Zoe. Just wanted to mention 4 things. First, that it's an autonomous vehicle. So like we see in the media today, self-driving cars getting themselves down the road without running into anything. This robot's able to do that, and in fact has been doing that for a very long time. One of the things that we have developed for TREX is a web-based interface, a collaborative interface. I'll tell you a little bit about that, and then I'll report on some recent progress on the development. So next slide, please. Zoe was designed as a platform to do this type of science work. It has, as I said, capability for autonomous navigation, but it also has things like a mast with pan tilt mechanism on which we can deploy a number of different imaging devices. We've used lots of different camera systems, 2, 3 camera systems, lasers, a couple different spectrometers. So it's configured so it's easy for us to do that. We also are able to deploy sensors up from underneath the robot. There's, again, a large variety of instruments over the last 15 years, but moving sensors, deployable sensors, we've had chemical things that spray on the ground. We've had imaging devices. We've had manipulators that reach down and grab stuff. And all of this is powered by a solar array on the robot, which is very high efficiency. And in fact, we've never had to augment the power of the robot. It's always had plenty to operate all these instruments and drive around. Next slide. Just quickly again, lots of experiments in its early days, just trying to make autonomous navigation work. But at this point, we're able to travel kilometers at a time, fully autonomously. I think we got tired on our long distance run after 14 kilometers and just decided to stop and go home. So we're hopeful that this system will work well for TREX. Yeah, keep the distance under 10 kilometers, which should be good. Next slide. Development for TREX has been an interface that's, we hope, will foster collaboration among a physically distributed team with lots of different interests. So we've built a browser-based interface using the Google Map engine that allow the science team, you can jump to the next slide here, to work collaboratively, so everyone can enter data, can click and drag and put their ideas of highlighting locations that they think are important, highlighting regions that they think are important. So to use this as a tool to collect information about where they think the robot should focus its investigation, and information to give it to order to make decisions about where it should choose its samples. So this is just giving you a sort of, it's the Google Maps kind of view. You drop the pins. The next slide, it shows you can connect things together if you want to prescribe a path. You can also indicate what actions you think would be appropriate in a particular site or in a particular area. And we've had one ORT with the team operating this to plan out an exploration for the robot, and I think that went pretty well. We're going to get back to that now that well, things we went through a slowdown here with everyone, but this tool looks like it's ready to go. Next slide. Just to mention quickly, we do have an ASD spectrometer on board, and this is good. You can stay here. One of the capabilities of this robot is to automatically point and collect data with that spectrometer. I like to say this is like shooting from the back of a horse while you're riding, right? So the robot rolls along and you can pick targets, and it can actually track the targets and keep the spectrometer pointed at that target and collect data. Next slide shows last week in our lab.
Wait. No, wait, sorry.
That's okay.
I don't know what happened. Wait.
That's okay.
There. Okay, hang on. There. Oh, Does that go to a movie, David?
I think the movie should be embedded, but it's what would be seeing if the lights hadn't gone out in the lab, I guess, is
presentation mode. You might be able to be just play outside presentation mode, Amanda.
Okay. Hang on. Sorry, let me just get it out of presentation mode. Okay. And then
Bummer.
no, I thought it was working before. I don't know why. Well, can you share what we should be seeing?
Yeah, sure. In fact, if you can just show the still image, and I'll wave my hands like it's moving. But
Okay.
what you see there is the lab. What we were doing was completing the integration of tetracorder onboard Zoe. So there's Zoe. It's up on a rack right now. In the next slide, you'll see a close-up of the four optic of the ASD spectrometer. And in the movie, what you'd see is this spectrometer moving around, and then I pan down and we've got some rocks, and actually it's rocks in front of a big bush, and we're collecting spectra of those. The next slide, I think includes the movie. You can sort of see behind there you go, that one's working. There's our spectrometer. And before we zoomed in, you could see there's a white reference on the back of the robot, and it periodically, the spectrometer spins around and checks the white reference, and then it automatically turns back and starts shooting spectra of the target. In the background there, two of my PhD students, Srinivas Vijayarangan, and who's been doing a lot of the autonomous navigation work on the robot, and Alberto Candela, who implemented that deep learning network that does the reconstruction of high resolution spectra from the prior measurements. The next slide shows tetracorder. Sorry, this is the best we could do on short notice, but really what's happening here is the latest version of tetracorder that Roger was just describing are running on the processor on the robot. So we collect spectra from that spectrometer. We record it to a data file. We transfer that to tetracorder. So then tetracorder runs, and instead of that simple classifier, now we have the full strength of tetracorder to do all the unmixing, to look at all the libraries and tell us what's there. And if the movie played, you'd see it start saying vegetation, 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 when that spectrometer points up and is shooting the bush behind it. So we're going to do better than that. We're going to get real geologic samples. But the important milestone here was to actually get tetracorder integrated with the rest of the system there. All right, so I'm basically done there. I think the next couple slides are just, again, for folks that aren't familiar with Zoe, you can flick through and see when we pull the shell off, we've actually got this large payload bay in which we can put all different kinds of instruments. And we're expecting a few more spectrometers from the TREX team. And we've got the space and the power to support those. And with that, I'm going to stop. And just remind you, so we've used Zoe a lot for these field experiments. We now have this rover commander that will allow the whole TREX team to collaborate when we're out in the field. We've automated for the one spectrometer with tetracorder. We expect to add some more spectrometers to that. And as soon as we can, we'll be ready for an experiment.
Great, David, thank you.
Thank you.
I'm going to go back to Eldar slides. Okay.
All right. So going from the rover to the instruments, basically, right now the plan is to have a set of instruments, some of which are sitting on the rover, are remote sensing instruments. Those are, of course, the navigation cameras and the science cameras, as well as the ASD, which is already part of the rover. We will also have on the rover a gamma ray spectrometer, which Tom will talk about in the next after this slide. Of the rover, we're gonna pretend the rover has an arm, which is basically somebody carrying these instruments, and we will have an ultraviolet spectrometer as well as the FTIR that Neil was showing you guys earlier this morning. These two instruments will be contact instruments. They will basically, the rover will make a decision of where to place these instruments on the rock, and these instruments will take measurements of those specific spots. And finally, we'll have a sample analysis instrument, which is the XRD, the portable XRD that Neil was showing you guys in the PSI lab. that will be taken out to the field, and XRD data will be collected of specific samples that are selected by the rover to analyze. Okay, so all of these are commercial instruments except for the GRS. So I'd like to Tom to give a short talk on the GRS and its capabilities. Tom.
Hey, Eldar, GRS coming at you.
Okay, just a quick sec, bringing it up.
Okay, next chart. Okay, so I'm going to give a brief talk about radio element geochemistry with gamma ray spectroscopy. This is work that we're doing with Dave Banneman and the TREX team. And so planetary applications are numerous for just measuring the radio elements. These are 3 elements: potassium, thorium, and uranium. Thorium and uranium are diagnostic of accessory minerals in silicates, for example, and potassium is diagnostic of, well, potassium-bearing minerals, and these can be through a variety of processes. For our project, it's possible to get an estimate of potassium if you know the mineralogy that you'll get from other instruments on the rover, so we can do some intercomparisons. And there are a variety of processes where these elements are important: silicic volcanism, weathering, and aqueous alteration. Next. And then these are just the signatures we have. For example, these are lunar gamma ray spectra on the right. You have pulse height in MeV, so this is the energy of the gamma ray produced by the decay of the radio element. And count rate, so you're looking at a spectrum, and there's the blue and the red and the green arrows are pointing to the major gamma rays that are made by the decay of the 3 radio elements. The main reason I wanted to show you this is that when you're on the moon and you have cosmic rays all around, basically what's happening is you're producing a lot of other gamma rays associated with other elements. Next. This makes it difficult to get at some of these radio elements. Uranium in particular on the left requires deconvolution to get at its intensity. Nevertheless, you can make a really super nice map of uranium using the high resolution gamma ray spectra acquired by the Kagoya spectrometer. Next. When you go to Earth, the cosmic rays go bye-bye. So no cosmic rays, just the radio elements. And so I do not have to worry about using high purity germanium. And so I'll spare you a little bit of grief looking at this complex eye chart table. For field work, we don't need germanium. We don't need any fancy new technologies. In fact, the technology that works the best, and I'll hold up, oh God, it's heavy. This is a detector. I'm exaggerating to emphasize how heavy it is. You can make super efficient detectors using technology called BGO, bismuth germanate. It is the gold standard for Earth applications in terrestrial geology, particularly oil well logging. So that's what people use. There are some new technologies that I recommend never using. Yeah, please.
Can you show that again? I didn't have your video, your
There'll be a picture. There'll be a picture of it later.
Okay.
So let me just continue on. There's lanthanum bromide. It's a mess. It produces a lot of self-activity that overwhelms the signature that you want to measure. And in our lab, we have cerium bromide and strontium iodide that offer higher resolution spectra than with BGO. Still, it's the BGO that we're going to implement on the rover. So let's go to the next chart. Currently, in the state of New Mexico, COVID-19 restrictions preclude us going anywhere else. If we go interstate travel, we end up having to quarantine. But we still need to build our instruments, test our instruments, and sharpen the saw to prepare for TREX rover experiments. And this has motivated some field work. I'll point out that the initial field work was done before the pandemic, but we are planning to return. So one of the things that we're doing, this is a map of northern New Mexico. LA is not Los Angeles, it's Los Alamos. SF is Santa Fe. And so our field study for the project I'm going to talk about is the Espanola Basin, which contains conglomerated alluvial fans. And these fans formed back in the Miocene when it was wetter in New Mexico. And what's really cool about that is that you had these ponded areas and camels and animals like that would visit. If you had a distant volcanic eruption, the ash from that eruption would get trapped in these ponds, and then it would form a sedimentary layer. And these tend to be silicic eruptions. They tend to be rich in radioelements. And so this is an ideal place to go and test out the gamma ray spectrometer for the rover. Okay, so let's keep going. And so one of the things, so basically what we're doing is we're going to northern New Mexico to classify volcanic ash beds. And on the left, I have a chart of potassium versus silica. Ideally, this would be total alkali versus silica, but it's potassium versus silica. I don't have the silica, but I do have the potassium, and I can use a potassium as an indication of the type of volcano that I had, the type of volcanism that I had. And then on the right are the X-ray diffraction measurements that Dave Banneman made of samples from this region. And we measured specifically with GRS the samples A1 through 3 with the green, blue, and red arrows respectively, which we'll see in a second. And we also measured the surrounding Tasuki sandstone formation. And most of the potassium that's in these volcanic ashes is in the form of glass. So as an amorphous phase, you would never see with the reflectance spectrometer. So it's bringing, the GRS is bringing an extra parameter that may help us understand the geology of the sites we look at. Tasuki formation is a bit more complicated. It's a mixture of glass, clays, and potassium feldspars. Next chart. And so there we are out in the field mapping with GRS. On the lower right, there is the gamma ray spectrometer. It's on the end of a high-tech cart, high-tech. It's a golf cart. It's on the end of a golf cart, which, by the way, turns out to be ideal for field studies. And Dave Banneman is pulling the golf cart over this rugged terrain. And you can see the ash beds. There are these white deposits. And you can also see the Tasuki sandstone formation. So we marched all along these ash beds. And as I mentioned, there were places indicated by the colored arrows where we'd actually taken samples and done XRD. And so what you can do here at on the top left within A, these are the spectra, BGO versus strontium iodide. It's pretty clear that the information content from BGO is similar to that of the strontium iodide, even though it has lower resolution. And there are 3 spectral bands that give you the 3 elements that are of interest. And so we marched along this terrain. We geolocated ourselves with GPS. And we made a map, a heat map of what we saw, but that's easiest to see on the left in B, where you have counts versus measurement number for the 3 bands I mentioned, potassium, thorium, and uranium. And you can see that for the 2 samples where indicated XRD suggested higher potassium content, indeed you have higher counts. And the 3rd sample, which is lower, yeah, you have lower counts. So let's move on to the next and final chart. So, so basically what we found in this preliminary study is that the gamma ray counting data and the XRD derived potassium concentrations show consistent patterns. And that's really good news because we can use them together as part of our field study. And then the XRD reveals a significant glass component, which is the primary bearing phase, potassium bearing phase in the volcanic ash. And so potassium content that we measure with GRS can be correlated with the abundance of silicic ash in this region. And so the future work is going to test the use of these elements for discriminating ashes from multiple volcanic sources. And then on the right, to finish up, is sort of the paradigm kind of imagined for rover studies. And I believe that Eldar would be doing the XRD, but I think he might also get some help from Dave. I'm not sure he can comment on that. But basically, when you're out in the field, the GRS will be attached to the rover, and it will be continuously sending a stream of counting data that will be interpreted in terms of elemental abundances. This goes to a science team, and the science team interacts with the astronaut. You can take samples, and the samples can be analyzed by XRD, and decisions can be made on what to do, and interpretations as well. And then after the fact, perhaps long after the fact, we can take these samples back and look at them more closely with a high resolution wall counter and validate our experiments. So that's all I had for that.
Thanks, Tom.
Great.
All right, let's move back to the.
Okay.
Okay, so now we have all the tools. We have the hypothesis map. Am I talking? Yeah, we have the hypothesis map. We have tetracorder. We have the rover. We have the instruments. Amanda, can you bring back up my presentation, please?
I am working on it. I am.
Thank you. Next. All right. So So all of this comes together to go into a useful field campaign, right? So what the objective of the field campaign at the end of the day is actually to compare the science yield and operations efficiency of our current robotic exploration strategies, basically the modern paradigm, with that of the semi-autonomous robotic system that uses the hypothesis map, and also with a strategy that has an astronaut in the loop. And depending on who you ask, this could be astronaut-assisted rover exploration, which the astronaut office does not like, or it could be a rover-assisted astronaut exploration, which is more like what we're trying to make happen here. Okay, so we're gonna be in the field for a total of 4 weeks over a span of 2 years, 2 weeks on 1 year 1, 2 weeks year 2. And the field work is going to be performed at sites containing fine-grained materials to at least basically have some degree of analogy to other fine-grained particular surfaces. We were considering 4 different locations initially, but we have basically narrowed down to 2 locations, 2 regions in which there are several sites. The first one is the Hopi Volcanic Field in Arizona, and the second one is the Yellow Cat Graben in Utah, which is just north of Arches National Park. Next, please. So this is basically the Hopi Buttes region of Arizona. On the lower left, you see Flagstaff. Towards the right, you see all the, basically right off center, towards the bottom, you see all those little pimples, dark pimples. Those are the Hopi Buttes. And basically, square numbers are different sites that we are considering. We plan to go to 3 sites. Well, most likely 2 sites, but we'll try to add a third site during this during the 2 weeks we go here. And then we'll have 2 backup sites in case the other site, some sites are not working out. So the first site on the left side is basically the intersection of a lava flow with pre-existing sedimentary units to be able to see, basically to explore the interaction, a region of multiple layers of different geologic origins. Number 2, which the box should be a little higher up, is that purple smudge that you see there, which is basically a geologic window into the Chinle Formation, which is a formation that stretches from basically our western Arizona all the way east to Texas and all the way up north to Wyoming. So it is a humongous, geologic unit on this planet, and that there provides a geologic window. 3 is a backup for 2. And 4 is basically one of the Hopi Buttes, which once again are volcanic necks or volcanic lava flow that's highly eroded. That's also seated on top of other types of geologic units. And 5 is basically a backup for 4 or vice versa. So let's go to the next slide, please. So this is basically what number 2 would look like. It's basically, you can already see at a small scale, you can see a little brush there. You can already see that there's quite a lot of layering on these slopes. The idea of the layering like this at small scales is that although it cannot be seen in aerial data, you can definitely see it from the ground. So if you're a geologist, you would notice these layers and walk up to them and explore them. So the question is whether or not this semi-autonomous rover exploration would be able to detect this, and how fast would, and basically study them autonomously, and how fast it would accomplish so. If you're in the modern exploration paradigm, you'd have the scientists see that And then they would spend a lot of time basically telling the rover to go to each of these layers. So the idea is basically to see if the rover can actually perform some, improvised science here. Next one, please. Here's a more of the same. It's a backup site for the previous one I just showed you. Also, a lot of fine-grained layers of materials. Go next, please. Here is basically the contact between the lava flow of the top part of that box and several different units, including that reddish unit that's just on the left of center, and then a tan unit that's also bottom right of center. Basically, there's a lot of different layering. There's some Easter eggs in there to see whether even the astronaut is able to see the Easter eggs that we found there. So we have done some geologic studies here. There's an extensive literature here on the geology of these regions. So we know what we're supposed to find here. So we're gonna see how much of this knowledge envelope or knowledge container is filled in by these 3 different paradigms. Next, please. This is basically what the Hopi Buttes looks like. On the right-hand side, you see the top of one of the buttes. The slopes are very steep, full of rocks, providing some kind of challenges to navigation. But then there's some interesting contacts with sandstones and other fine-grained materials right under it. So the questions here are whether the rover is actually, whether there are settings in which the rover would probably not be as efficient as having a human basically guiding the rover by hand practically. So this is one of the things we want to explore. What happens in situations where it's difficult to navigate. Go on to next, please. And the last site here we have is this amazing volcanic fissure, which basically erupted and spewed out a lot of volcanic ashes off into the distance. So you can actually drive right into this fissure and look at this at the cross section of the fissure in many places. And there's been some excavations there, so there's a lot of goodies to be explored there. So that might be one of our backup sites. All right, next, please. Oh, and in year 2, we plan to go to the Yellow Cat Graben, which is north of Arches, and this is basically an aerial shot of one of the sites, and you can see that there's already in the just in normal imagery, there's a lot of diversity on a rather small scale. On the left, there's a road for a scale, so you can see that at scales of just a few meters, basically the terrain varies in mineralogy and color very, very drastically. So this will be kind of like a box of candy for rover exploration. All right, next, please. All right, so what operational scenarios are we comparing? Well, like I just said, okay, actually we can skip this because I already said this. Let's go to next. All right, so this is what it looks like. In your standard paradigm, basically, you have the operator sending commands to the rover. Rover, move forward 1 meter. Take a panorama. Okay, the operators go study the panorama, and then they go back. Okay, rover, go to that rock there and take a picture of this part. And in all these cases, there is a limit to how many to bandwidth. There's a bandwidth limit and also a data volume limit to how much observations they can request or how much total data they can request. So they have to be intelligent about how they can request. They cannot request, full spectral panorama of everything, for example. That's not something that would be possible. All right, and the next one on the surface looks similar, except that the little white boxes are very different. Basically, the operator sends the hypothesis map to the rover. The rover decides where it will go and what observations it will perform. The rover performs these observations and then contacts the operator with basically the results that it deems as the most salient of these observations, basically the things that answer the hypothesis map. Okay, next, please. And in the third one, basically, this hypothesis map exploration has been performed and several different sites have been selected by the operators. The operators contact an astronaut who has been hiding away in a habitation module so they don't have to spend the whole day inside a bruising spacesuit. They tell the astronaut where to go to collect samples, and the astronaut goes, perhaps with a rover. And as the astronaut goes, they also perform geology, basically. They're looking at the terrain, they're seeing if anything has been missed. They can also ask the rover to perform specific observations with the spectrometer and return results in real time. So that basically, the question is how much more science will having an astronaut in the loop actually provide beyond beyond what the rover was capable of accomplishing. All right, next, please. This is something we saw before, so I can skip this basically, but yep, let's go back again for a second. So part number one is basically where the hypothesis map is generated, right? So what does this look like in reality? Basically what we're planning to do here. So we have a group of scientists who've never seen this terrain before, and they receive high resolution aerial imaging of the area. They receive topographic maps of the area, and they get hyperspectral data cubes from basically in the infrared from AVIRIS, which is the infrared airborne spectrometer, and ASTER, which is an infrared thermal infrared one. The scientists then analyze the data and create the hypothesis map. So let's go to the next one now. So, oh, the other way. So data analysis can have different ways, right? If you're a spectroscopist, you could choose to do some spectral math. For example, you know that there's a specific absorption, for example, that corresponds to a specific mineral, right? At 2.3 microns, there's an absorption. So you basically, for every pixel that is a spectrum, you actually calculate a parameter for the 2.3 micron feature. How deep is the feature in that region, right? If there's no feature, the parameter is 0. If the feature is very deep, the parameter increases to a value of 1 for full saturation. So the leftmost picture is the map of one of the sites, site number 2, the purple spot over there. And then each one of the images to the right of that are basically maps generated by playing this spectral math game, looking for different features and looking at the band depths. In this case, these are band depths that we use for CRISM on Mars, which is interesting that they return stuff here too. And you can see that some places come out bright in the yellows, having higher band depth, and other places come out lower, having a bluer band depths. So as a scientist, you could say, well, some of these regions would be interesting to actually go and explore directly. All right, next, please. Another way you can do it is play the tetraquarter map. You ingest the entire data set into tetraquarter, and you have tetraquarter spit out specific mineralogies. So in the case, once again, we have the same region, but in this case, tetraquarter has mapped out the distribution of what it thinks is pyroxene in those red spots. Other places where it thinks it's found calcite and kaolinite combinations, and other places where it's found kaolinite. Now that we actually have actual mineralogic origins, next please. You can take the spectral feature to constrain the minerals, basically in the leftmost column to the middle column, right? Which is what tetraquarter does. And then the rover takes it to one more step forward, or we take it one more step forward when we create these maps, which is the geologic origin. Some minerals have unique geologic origins. For example, the mineral pyroxene, which can be detected by the broad 2 micron band, is uniquely igneous. You cannot form it by any other processes. So basically it's unique. However, there are other minerals, for example, saponite on the bottom, which can be detected by a sharp 2.3 micron band, has multiple potential origins, can be hydrothermal, fluvial, lacustrine, or marine. So you can already see that detection of some minerals is entirely unambiguous as to geologic origin, where others present a high level of uncertainty in their geologic origin. So this is where we start looking into the uncertainty. Go next, please. So usually a single mineral, because a single mineral can have several different geologic origins, what you look for is usually mineral assemblages. So basically, if you have minerals A, B, and C, which the 3 of them are hydrothermal, all of them have a hydrothermal origin, basically that increases your probability that the site is hydrothermal. So what does this mean in this case? So what we create here is instead of a hypothesis map, it's more of a hypothesis cube. In this cube, basically the X and Y spatial dimensions, basically the map, the dimensions, and every plane is a geologic origin hypothesis. So every pixel basically will have a value between 0 and some number, whereas every time tetraquarter has detected a specific mineral that has a specific geologic origin, the pixel value goes by 1. For example, in the case of the pyroxene, the pixel number of the igneous map goes up by 1, but none of the other ones get values for that one. On the other hand, when you find saponite, where you could actually have any of these other origins, basically each one of those, the pixel for each one of those other planes goes up by 1. So in the end, you basically have different image planes for different types of geologic origins, where the value of the pixel value is the probability of geologic origin. The more minerals corresponding to that geologic origin, the higher the pixel value is going to be, right? So the rover's job is going to disambiguate the geologic origin for each terrain. Go on for next, please. So basically, looking at the same map we had before, this is an example of our geologic origin planes. And you can see that there are many terrains. There are several terrains that actually have multiple geologic origin explanations, right? All the material on the right can be lacustrine or pedogenic or igneous, right? And then the material on the left is most exclusively evaporitic in this interpretation. So basically, your likelihood increases with the pixel value, as I stated before. And you can see in the igneous one on the rightmost, there's some very bright white spots, and then there's some very dark spots, basically. And that tells you where the higher probability of finding igneous deposits is. Now, we have to talk also about the uncertainty. So in the case of the terrains on the right, there's 3 different possible origins for those terrains. So their uncertainty value increases with how many terrains are possible for that specific pixel. So we now basically have a likelihood of the origin, but also a degree of uncertainty. So knowing this, go on to the next one, please. We basically start considering, we basically feed this maps to the rover. And for the rover, this becomes an optimization problem. Basically, it wants to reduce the amount of uncertainty for any one of those terrains. But at the same time, it also wants to consider the distance and accessibility of the terrains, right? So the rover basically maps out some kind of pathway. So the yellow line would be the rover selected route, for example. The circular spots are waypoints where the rover plans to go to perform its analysis, to stop and perform its analysis to look for minerals that would basically disambiguate the uncertainties. And then basically the diamond shaped, the scientists say, no, you must also go to these terrains because we can see in the pictures that they look really cool. There's something there we would like to explore. So we include those into your rover. So then number 4 is basically the blue line. The rover updates its original path to include the scientist's requested waypoints. And prescribed, so basically at each one of these waypoints, the rover stops and basically performs an in-depth analysis, an in-depth study. It may make a spectral panorama, which it may not be able to entirely return to the science team, but it will be able to identify mineralogies and return those results along with, representative spectra. And as it's driving around, the rover can also be performing prescribed observations, maybe perform one spectral acquisition every 2 seconds as it's driving. Whatever scientists think would be a useful way of exploring that. They might not get the spectra back, but the rover can use it to basically see what's in between waypoints. All right, next, please. And of course, if it finds something in between waypoints that's interesting, for example, it finds a mineral that predicts a certain geologic origin, which was a certain geologic origin that was not supposed to be applied for that pixel, the rover could say, well, I just found something that was not expected here. I'm going to stop here. I'm going to contact the operators and tell them, hey, I just found something unexpected here. The operators can then look at the data and basically update their hypothesis map and send it back to the rover. So that's where the loop comes in. So what parameters are we comparing? Here's the metrics. We actually need to be able to have some sort of degree to understand which paradigm will be more effective. So as far as operational efficiency, basically how many sites can be visited on a specific period of time, distance covered. And of course, this is not real time. This is simulated time. So artificial penalties apply for simulated activities. For example, sample collection by a rover or an astronaut have a specific time penalty because a rover would be slower at collecting samples than a human. Contact science also imposes an artificial time penalty. In real time, we're going to have a person walk up to the rock and put the spectrometer on the rock. But that could only take 2 minutes in real time. but in simulated time, that could be a process that takes hours because a rover can take hours to accomplish such a feat. The other parameter we're comparing, of course, is science yield. Basically, which one addresses the hypothesis and presents a consistent picture of the geology and the stratigraphy, and also which finds targets of opportunity that actually enhances the science that was performed. So those are basically our two metrics. Next, please. We were planning to go at the beginning of this year in the April-May timeframe, but due to COVID, we had to cancel. We were then planning to go again in November. Basically, we would have been there 2 weeks ago or a week ago.
Eldar's frozen.
Yeah, he's frozen for me as well.
Okay. We'll see if he comes back. I'll fill in. We were tentatively thinking of going in November instead. Oh, here he is. Okay, great.
There you are. Oh, interesting. My power went out. Okay.
Okay, so now we're tentatively thinking of going a year from when we originally had planned. So late April to early May of next year. So here's the plan, the kind of our itinerary. We will have to just see how things go. If COVID still looks bad, maybe we'll have to reschedule for later next year. But hopefully, knock on wood, we'll be able to go next year. And then TBD on when we would go to Yellowcat. I'm just going to keep going here a little bit because I know we're a little behind schedule. Oh, that's the end of the show. Hopefully, Eldar, are you going to come back?
Yeah, basically that was.
Oh.
Yeah, I just came back on my cell phone.
Oh,
Can you
okay,
hear
good.
me?
I just summarized
Yeah,
kind of the itinerary and how we'll see how things go.
Yeah, that's perfect. We'll see how things go. New president, new time. Maybe things will be better by April. Maybe not. So we have to keep our eyes open and see
Yep.
where it's going.
Yep.
And that's it. Okay.
Okay,
Back to you.
great. So Eldar, David, Tom, thanks so much for great theme for presentations. I think this is really exciting. I'm super excited all over again about going out into the field. I hope we get to go here pretty soon. I know that we are running late. I'm sorry we're behind schedule for everybody in the audience. Thank you for hanging in there. Does anybody have any questions or comments for the fieldwork crew? I know it's past 6 o'clock on the East Coast, so I am trying to be sensitive to people's private lives and everything. But I will say that concludes our TREX site visit, virtual site visit. I really want to say thanks so much to the TREX team for excellent presentations and preparation. And I think this has been really fun for everybody on the team, but it's also been fun to have everybody on the other survey teams and headquarters folks hear what we've been doing and get some collaborative ideas going. So thank you everybody for being here, and let's just kind of continue the conversation by email. I'm sorry we can't all go out to dinner now, but maybe next year sometime. So I guess we'll just say goodbye and take care, everybody. Stay safe, and thanks so much.
Amanda.
Thanks, Amanda. Fantastic job.
Oh,
Thanks,
great.
folks.
Hi, Greg. Yeah, there you are. Thanks.
Yeah, I really appreciate it. You guys really kicked off this whole idea of virtual site visits extremely well. It was an experiment and it was a successful one. So, so thank you. Thanks to everyone.
Yeah, thanks for being here and hanging in there. I'm sorry we went a little long, but just a lot of good stuff to talk about. So